So, look, I know what's on your mind is the final exam, which is on Monday, right? We all know that, I hope. And here's where I need you to go. Some of you are going to come here, and some of you are going to go to the Dinkelspiel auditorium. It's over there, right? I think. And if your last name, your family name starts with A through G, I want you to come here. And if it starts with H through Z, you go to Dinkelspiel, okay? It'll be Monday morning at 8:30 a.m., bright and early. I strongly recommend that you set a couple of alarms. If you oversleep, you're just basically eating into your own test time. I don't give you extra time at the end if you show up late. So please make sure to set lots of alarms for this coming Monday. It's going to be real early, right? Sorry about the crappy time. That's like, they gave us that time every quarter. Somebody over in the university offices does not like the CS department. They don't like scheduling our exams or something, so they always give us Monday morning at 8:30 a.m. And there's always one guy who shows up an hour and a half late, sweat streaming down his face, and he's like, I'm so sorry, I overslept. And don't be that guy. Set like 4 alarms. Set your neighbor's alarm, set your roommate's alarm, tell your mom to call you at 8 o'clock, like whatever it takes. Get up on time, get to the test, okay? So what I want to do today is I want to talk a little bit about the exam. I mean, you guys have probably already been looking at some of the practice materials, but I just wanted to take a couple questions or answer a couple things about the exam that's coming on Monday. And I wanted to kind of wrap up the quarter and talk a little bit about kind of a summary of some things that we've learned and stuff like that, okay? That's the plan. So let me jump to the exam portion of the web page. So we got like 3 practice exams posted here. I'm going to post at least 1 more practice exam over this weekend, probably tonight, in case you want some more problems to study from. There's also more problems in the Code Step-by-Step site if you still need more practice, okay? I would say if you look at all these practice exams, the kind of problems I will ask you on the real test are going to be these kinds of problems. I'm not going to throw a curveball at you and ask you a totally different kind of problem that you've never seen before. So if you look at these practice exams, I think that'll get you kind of ready for what you're going to face. There's a list of topics here that you need to study. The exam is, people have asked if it's cumulative or if it's on the material since the midterm. I mean, it's definitely on the material since the midterm, but a lot of the stuff you learned before the midterm is still needed. Like, you still need to understand recursion, you still need to understand pointers, you still need to understand the collections, the ADTs that we learned, but you're using them to solve these new kinds of problems that we saw after the midterm. So these are the main topics I would test you on. Linked lists, binary trees, backtracking, implementing collections, graphs, heaps and hashing and searching and sorting and inheritance. A lot of the stuff at the bottom here is the stuff that we've covered over the last week and a half, kind of after assignment 7 went out here at the end of the quarter. So yeah, that's basically the set of topics. There's some things that we guarantee will not be on the test down here. I always like to reward people who come to class, so I will answer at some point during today's lecture. I will tell you a couple of problems and whether they will be on the test or not. And I will turn the video off for those moments. So the people who aren't here, they won't know. Or I guess they won't know unless you tell them, so don't tell them. So that's a set of topics. I mean, I think if you look through these exams, you'll get a sense of the kind of exercises that I'm likely to ask you. I mean, if you just look at the first one. Wait, how do I? Hold on a sec. 6B exam. I know. I haven't been teaching that much lately. I kind of forgot how. I'm like, where do you go? Oh, you stand up at the front of the room? Oh, okay. So, practice final 1. This is a decent sample to look at. There's a searching and sorting problem here. I ask you about binary search. I ask you about selection sort, insertion sort, merge sort. Those are the 3 sorting algorithms that I would potentially ask you about. I won't ask you about quick sort or BOGO sort or any of those other ones. There's a linked list mystery problem where I give you a linked list of data and I give you a piece of code and I say, what does it do to the list? So I want you to traverse through the code and see what it does. There's a linked list code writing problem where you're given a front of a linked list and some sort of operation that you're supposed to perform to the list. So it's likely that you'll get a question like that on the real final, right? Binary trees. I have binary tree reading questions and binary tree writing questions. Of course, we want to be careful to differentiate between regular binary trees and binary search trees, right? Binary search trees, the ones that are sorted from left to right. And so if I tell you that I'm going to add these nodes to a binary search tree, I want you to show me that you're going to put the smaller values on the left. In this case, that means earlier in the alphabet on the left and later in the alphabet on the right. I have had students who were very stressed out during the test and they couldn't remember the order of some of the letters of the alphabet. And you laugh, but it'll probably happen to some of you on Monday. So, because I love you guys, I will put the letters of the alphabet up here. I will write them out for you. Let it not be said that I wasn't there for you when you needed me. Yeah, so case insensitive, alphabetical order sorting. So I'll ask you to add things to a binary search tree. I might ask you to traverse the tree. I might ask you to remove some elements from the tree. Sometimes I like to ask you if the tree is balanced or not. So if the left and the right sides are roughly equal size. So I like to ask questions about that. Take a look at the different practice exams to get a sense of the kinds of things that I would be likely to ask. Was somebody's hand up? Interrupt me at any point if you have questions about this stuff. Yeah, go ahead. You don't need to know about how to write the AVL code that rebalances a tree, that rotates a tree, or any of that kind of stuff. No. I want you to understand what balance is. I want you to be able to look at a tree and tell me if it's balanced or not and why. But that's it. I don't want you to have to fix it to make it balanced. Any other questions so far about the linked list stuff, about the binary tree stuff, anything else I've said so far? Yeah.
When you say balanced, do you mean complete?
No, I don't mean complete. I mean balance where like the height of the left versus the height of the right. If those are within one of each other, it's balanced. And that same property has to hold true all the way down the tree. Yep. Yeah, in the back. Yeah, difference between binary tree and binary search tree. Basically, a binary tree, just binary tree, the values in that tree could be in any order or any arrangement. The values on the left don't have to be smaller than the values on the right. The values on the top don't have to be smaller than the values on the bottom. I can just shuffle around the data and put any data anywhere I want. But a binary search tree, they do have to be sorted kind of left to right. So a lot of times when I ask you to read code for a binary tree, I do it with a binary search tree like this. And the reason I do that is because there's a clear answer. Like if I tell you to add these values to a regular binary tree, you could add them anywhere. So this only has a clear single answer if it's a binary search tree. When I ask you to write code, it might very well be a regular binary tree that is not a binary search tree. Like in this example here, if I remember correctly, there's no particular ordering to the numbers in the tree. The ones on the left are not the smallest necessarily, and the ones on the right are not the largest. They're just a bunch of numbers. I want you to search through the tree for something, swap the children or remove the leaves or something like that, you know? So, yeah. So I am likely to ask you a question where you are writing code that processes a binary tree of ints, binary tree of strings, something like that, some kind of simple data. And I'll pass you a root of the tree, and I'll tell you to do something to it. Okay? Often, these are recursive functions because we process trees recursively. So if you're stuck on these problems, make sure you're calling your own function recursively at some point in your code, right? Okay. Binary tree writing. I may ask you about heaps. You programmed a heap, so you should know the heap has the vertical ordering, the top to the bottom, or the parents are smaller than the children. Or if you think of it as an array, the earlier indexes are smaller than the later indexes. So I want you to show me that you can do that bubbling up and down stuff when you add and remove elements. Basically just adding and removing from a heap is all I would ask you about heaps on the test. I will not ask you to write code for a heap. I will just ask you to read code for a heap. Graphs, I might ask you to look at a graph and answer some questions about it. A graph reading problem. Sometimes I show you a picture of a graph and I ask you questions like, is it directed, is it weighted, is it connected, is it cyclic, these kinds of things. Just general properties of a graph. Sometimes I ask you to show me the representation of the graph, like part F there says write an adjacency list of the graph, write an adjacency matrix of the graph. If you don't remember those, go look at the lecture where we talked about graph implementation. Sometimes I'll ask you to trace through what would happen if you did a search on the graph using Dijkstra or BFS or A-star or something like that. Yeah?
Maybe
Oh, on one of the practice problems, it uses a terminology called weakly connected or strongly connected. I won't ask you about that on the final. If you want to know what those terms mean, basically weakly connected means that you have a directed graph with the arrowheads on the edges, and if you made it undirected so that the edges went both ways, then the graph would become a connected graph. If that is the case, then you have a weakly connected graph. Strongly connected graph means it's already connected the way that it is. But I won't ask you that. I will just ask if it is connected or not. And so basically, if it is any of those kinds of connected, you can say yes, basically. In the back, yeah. That's a good question. Yeah, usually for A star, you know, if you remember that one from Trailblazer, you know that a heuristic function is an important part of that algorithm, right? So if I'm going to ask you to trace through A star, I have to tell you what the heuristic function is. So, you know, if you're going to have to trace through A star, I'll have to say something like, the heuristic would be this times that or this plus that. I'll have to give you some sort of way to know what that heuristic value would be. Now, if you say, I don't quite remember how A star works, the entire algorithm of A star will be given to you as pseudocode on your reference sheet. You can go look right now on the exam page and you can see what's on the reference sheet. It does have all the graph algorithm pseudocode from Trailblazer on it, in case that's useful to you. Yeah?
About what you said about connectedness, say we have a graph with two nodes and there's a direct edge from one to the other, do you consider that to be connected?
Yeah, I mean, the thing is then that A could reach B, but B cannot reach A, right? So I'll try to make clear what I mean if I ask you about connectedness. If I want you to consider direction of edges, I'll say so. And if that were the case, then a weakly connected graph like that wouldn't be connected. But if I don't care, I'll say, you know, just assume the graph were undirected. Would you say that it's connected or not? Then you can answer, then that one would be connected in that case. Yep. Okay. So yeah, that's graph reading. Then graph writing would be some kind of function where I pass you a basic graph as a parameter, do something to it, you know, search for something or modify the graph in some way or calculate something, I don't know. Sometimes these functions end up being recursive. Not always, but sometimes. I mean, if you're doing this operation to a given vertex and then you want to do the same set of operations to all the neighbors or to some other vertex, you often want to have a recursive function that takes the graph and the vertex and whatever else as parameters. Maybe some of these problems have kind of a backtracking look to them where you're kind of searching and choosing and exploring and unchoosing until you find a solution. So, I mean, these problems are sometimes kind of a Trojan horse where I can ask you about recursive backtracking at the same time. So, you know, you may not need to be recursive here, but you might. It might be the best way of solving the problem. You can kind of tell if I want you to do backtracking because in the description of the problem, I'll say something like, you will need to try all of the possible things in order to find the answer to this. And it does not need to be efficient. And if I say stuff like that, that is what backtracking is. Try all the things and see if any of them works. So I'm probably basically trying to tell you that you should use backtracking, but I don't want to totally give away the game. So there you go. You can decode my cryptic instructions that way. Okay, so that's graph writing. It'll be using the basic graph, the same one from Homework 7 Trailblazer. The reference sheet has all the methods and all the things from basic graph, so you don't have to memorize those. The reference sheets are usually incomplete. They usually have the methods that are most common. But if you happen to know some other method that isn't on the sheet, but you know that method is there, you are allowed to call it. That's fine. If I listed every single method for every single collection, I would have to give you a reference pamphlet instead of sheet or something. It'd be too much paper, right? So that's graph writing. A couple other topics. Sometimes we have inheritance problems. These damn things, right? These ridiculous labyrinths of crappy code that you have to walk through. You know, you guys saw those with Ashley a few days ago, and you know, if I ask you one of these, it'll be the same sort of thing like this, where I have several classes and they have several methods declared. Some of them extend each other, some of them override other things, and I declare some variables and I ask you to do some function calls and see what they do. And then some of the function calls have casting on them as well. So, you know, I'm not going to reteach you that whole set of material. You should look at Ashley's slides and the video of her lecture. But, I mean, if you're doing these, you have to look at the types of the variables to see if the code compiles, and you have to look at the type of the object being stored to see what the code does when it runs. And if you're doing casting, you need to look at the casting type to see if it has the right method as well. So, you know, she taught you a set of steps to follow, and those steps will lead you to the answers on these. We definitely get a lot of student questions about these problems on Piazza the last few days before the test. So if you're looking through one of these and you're like, why does bar 4A print so-and-so? Just go ask us that on Piazza, and we'll talk you through it. We'll try to explain it to you. No, that's no problem. We're happy to help with that kind of thing. Once you've done a couple of these, once you get the hang of them, I'm not going to have any new tricks on the real test. So if you can do this on the practice test, you'll be ready for it on the real test. And the last one is, actually not the last one, but the next one is inheritance writing. That would be where there's an existing class that's already been written. I want you to write a subclass that extends it. And I'll say things like, you know, when you roll the dice, your thing should rig the answer to be greater than so-and-so. So, of course, what I'm trying to tell you is I want you to override the roll method. You know, I'm trying to tell you in English that I want you to override or implement certain methods in your solution to produce certain behavior. So if it's not clear from looking at one of these, like kind of what I'm asking for, you might want to peek at the answer to one of them just to kind of see what does Marty actually want me to write here. I've had a few students asking me about that. So just kind of testing your use of the inheritance class syntax. I think this particular practice exam doesn't have a hashing problem, but I'm also potentially going to ask you about hashing. I forget, does number 2 have hashing? Which one has hashing? Did I not give you a hashing one? I better give you a hashing one. Searching trees, hash. Okay, so test 3 has an example of a hashing problem. There was one like this on your section handout. I would definitely potentially ask you something like this, where I put some stuff into a hash table, draw the array, what would it look like? Draw the little linked list and what would be in each one, which elements would be stored where. If I did rehashing, where would they move to? That kind of stuff. Okay? Yeah, question?
So only reading and not writing.
You would like to know if I'm going to test you on hash writing as well as reading? I'd be happy to answer that question. Okay. So yeah, do you have any other questions about the exam, about what is fair game or not, what to study for, what, I don't know, anything? Yeah?
When we learned about inheritance in the review session of an Anthony project, there was a discrepancy on whether crashing takes precedence or compiler error takes precedence.
Question was, what if there's an inheritance reading question that it would not compile and it would crash? Which one is the right answer? The answer is if it doesn't compile, then it will never get to run in the first place to crash. It can't crash until you run it. So you would only say crash if it did compile successfully. So compiler error takes precedence over crash. Guys got other exam questions? Yeah?
Operator overloading. On the website it said you're not going to have to operator overload the single equals. Does that mean that we might possibly have to overload other operators?
Yeah, so there's a little bit of confusion about this bullet that you're asking about. It says we're not going to ask you to overload the equals operator, but some of the practice tests overload other operators. So the equals operator is the assignment operator. Like if you said int x equals 5, you can override that operator. I haven't talked about doing that and why you would want to do that. It has to do with pointers and memory leaks and garbage memory. And sometimes when you're writing a class, for various reasons, you need to overload that operator. And some quarters I get to that, I cover it and I talk about it. But I didn't this quarter. And even if I had, I wouldn't ask you a question on it. So I may ask you to overload an operator, but it will be something more like the less than to print an object, or an equals to compare an object. It'll be something more like that, one that you've seen before. Okay. You got any other questions? You guys feel ready for this thing? Ready to be done? Yeah. Oh, is there a question? Yeah, go ahead.
Are we going to have to write a .h and .cpp file?
You have to write a .h and a .cpp file. Well, if I ask you one of these inheritance writing problems like this here, I want you to write the contents that would have gone in those two files, but you'll just write all of it out on a piece of paper, basically. So, I mean, you essentially yes, but only on this kind of a problem. This is the only one where I would ask you to write a complete class. Okay, yeah? Oh, do you have to write like include? No, you never have to write that stuff. So just as long as you have the right code and declarations, kind of all that if and def and include and end if and all that stuff, that you can leave that part out. Yep. Will there be a file I/O problem? Well, probably not. I mean, I guess I should say I should be more specific. I don't think so. No. I do want you to process data, but I would pass the data into you as a vector or an ADT or something like that. So I won't make you use the IF stream on the test. Yeah. Yeah.
And what about any like standard recursive backtracking problems? Will all the like recursion be packaged in like graphs and like lists, or is it going to be like 9 queens type problem?
Oh, right. Let me click this button real quick. And that summarizes my religious and political beliefs. Okay. Oops, I don't know if the video picked up that part. Oh, well. Anything else? Oh, yeah, go ahead.
What do you think are good ways of practicing, like writing practicing graph problems? Because there's no code step by step.
You mean the graph read or the graph write? The graph write problems, I thought they were in code step by step. Are they not?
Oh, they are.
I think they are. If they're not, I want to add them. I think they are. Double check. The graph writing, I think they are. The graph reading might not be, but those are just kind of pencil and paper. I mean, that would be my suggestion is just go try them there. Or if you don't have them there, you can just kind of make a empty project in Qt Creator and make a graph and try to call your function on it. I want to say a couple things. I got about half of the class left. If you have more questions about the exam, you know how to find me and the TAs and the section leaders on the piazza. I'll try not to bite your head off too much. So I want to talk about a couple last things here. Lecture slides. I've got a deck kind of like what's next, like what could you do next, or what have we learned, or something like that. The first few slides here, I think I'm going to just race through. It's just like, hey, what did we do? I don't know. We learned about C++, I guess. We didn't really totally learn the language unless you did 106L, but you learned a lot of C++. So I think if some company is asking you what programming languages you know, I think you can say, I've learned C++. I coded C++ in a CS2 course, a 106B course. We learned a lot about data and collections. That's important stuff. A lot of classes, you take the class, you move on, and you never use that stuff ever again. But if you're going to code, you're going to be using all this data stuff a whole bunch. Every program is full of data. So you're not ever going to stop using lists or vectors. You're not ever going to stop using hash maps. You're often going to have recursive structures that you traverse through. So you're going to be doing a lot of this stuff. We learned how the data structures are implemented inside. We learned about trees and nodes and all this kind of stuff. I would say that for a lot of people, when you go out in the real world and code, you don't implement as many structures from scratch like we were trying to do, but you sometimes do, and if you don't know how, you're really stuck. So you want to know how things work. Also, I think a big part of it is you have to understand a little bit about how things are built so that you'll know, trade-offs of runtime and why is it when I print out that hash table, that hash set, it prints out in the jumbled order. You want to understand these things so you really know what you're doing when you use all these libraries. So we learned a lot about that. We learned about different algorithms, graph searching, sorting, permutations, traversals, lots of fun stuff. These algorithms are pretty fundamental. A lot of other problems come down to, hey, I need all the permutations. Where's that code I wrote for permutations, Hey, I need to do an in-order traversal. Wait, I think I've done that on a binary tree. We learned recursion. Recursion is really important. Some kinds of coding, you don't do much recursion. I've had some people tell me they don't really use recursion much in their life or whatever, but it's one of those things where when it's the right tool for the job, it's really the right tool for the job. And when you need it, you need it. And I find myself using it when I write web apps sometimes, because a web page is implemented as a document object model, which is a tree. And so you often have to recursively look for things in that tree. So I find myself doing recursion in the web. I'm writing JavaScript web code. I'm doing recursion. The last place I thought I would need it. So you learned about recursion and backtracking. We learned a little bit about OOP, object-oriented programming. I would say this is a very partial thing. We didn't really get too far into that. There's other classes later where you would do more. I think it's not just about learning the syntax of what is a class, what is inheritance. it's also like learning how, if you have a big problem, how do you break it down into classes and hierarchies to solve the problem? And we didn't really learn that at all. And I think there's other classes later, like CS 108, where you might learn how to do that. That's probably the skill you really need after this. Okay, I wanted to just talk briefly about some stuff you could do that you could do now if you wanted to. And some of you might already be signed up to do that because I already know it's after the registration opens. So the next couple classes most students might take in CS would be CS 103 or CS 107. And if you liked this class, the highest compliment you could possibly pay me and the staff would be if you took another CS class. That would make my day. I would feel that I succeeded, or at least I didn't break you. I know you might be waiting till after the final to decide that, but these are the next two that most people take. 107 is our next programming course. 103 is our first theoretical computer science course. And those two areas of CS are both very important. So we kind of have tracks of classes for each of those that you would take. So I wanted to briefly talk about these courses. I see, Ashley, you're in the back. I wonder if maybe you could come up to front here with me, because I'm going to tell you a little bit about these classes, but Ashley here has taken them, and she can speak a little more authoritatively on it than I can in some ways. So maybe I'll give you my quick assessment of what I think this class is, and then I want you to correct me and tell me how I'm totally wrong. Is that cool? Sure. Hey, so CS 107 is our computer organization systems class. You go deeper down, closer to the hardware. You learn more about how processors work, how memory works, how the code that you write gets compiled and assembled into a working program. You learn about the operating system at a little bit deeper level. And you learn something called assembly code, which is like the instructions to the processor that your C code or C++ code or Java code gets compiled into. So you go down, you go a level deeper. It's like the Inception dream within a dream or something like that. That's what 107 is on paper. I know that there are some people who think 107 is a scary course. Have you guys got a friend or somebody you know who's like, oh dear God, I'm in 107, help me, right? It has a reputation for being a challenging class. What I have heard is that one of the big differences, it's not that it's 10 times as hard as CS 106B, it's just that there's no layer. And as you probably know, the layer is helpful. They still have helpers, they have TAs, they have office hours, but they don't have this mob of section leaders at all hours of the night waiting to answer questions. And so you have to be a little more independent, finding answers to your problems and stuff. And so that can be challenging for some students. But my sense of it is that if you do well in 106B or X and you work hard, you can do well in 107 as well. Now, I say all that having never taken it here. I've taken a course equivalent to that somewhere else. I'd like to ask you, Ashley, tell me about CS 107. What's 107 like? Is 107 scary? Should they take CS 107? Go.
So for CS 107, for me, that was the class where I really started to understand pointers. Like I made it through 106B, kind of like, don't really understand this. I'll like kind of fudge my way through the pointer traces. We were allowed a note sheet, so my note sheet was just pointer traces because I couldn't figure out pointers. And so 107, you will learn pointers really, really well. If during the polymorphism lecture, you're like, wait, why does C++ just let you cast something to something else, even if it's going to crash? Like 107 is all about casting variables to things that they are not really in order to like figure out how the memory is laid out underneath, which is really cool. So you get to learn a lot about how memory works. You get to learn a lot about how to debug. You leave 107 knowing how to debug, which is a really cool feeling because it makes all of your programming exploits in the future a lot better.
How hard is it? Is it killer?
It was so. I know that the homeworks have changed a lot since I took it. So I feel like anything I say is inaccurate because like at least 3 of the homeworks I think have changed or changed order. But you get to learn how. Are they still doing C-vector and C-map? I thought that was one of the coolest assignments.
I think so.
Okay.
Yeah.
So if you're like, when I was talking about hash maps and Marty was talking about hash maps, if you're like, man, I really want to implement that, like you implement a hash map in 107, which is really cool. It's hard, but mostly it's hard because debugging is hard. And so if you like don't know how to debug, that's what makes it hard. Like conceptually, I don't think it's super hard. It's just C is not a language that has friendly error messages. Like if you remember from 106A when it was like Java is giving you like an array index out of bounds exception. Like the equivalent of that in C is like basically they give you nothing and it just crashes and there's no information on why it crashes. So that's the hard part about 107, but it's not conceptually like a super hard class. It's an interesting class, but it's not like a lot of the concepts in 106B I found harder than the concepts in 107. It's just debugging is hard.
We should both go into marketing, shouldn't we? Look, and in terms of if you have goals of things that you want to do, things that you want to learn, our curriculum here in the CS department, 107 is the prereq for like everything. And so, if nothing else, at least taking 107 really unlocks a whole bunch of other awesome classes that you might want to take after 107. I think 107 itself is also quite interesting. I think, as you said, it really unlocks kind of the mystery of like what really happens when I do this or what's going on underneath this code that I wrote. You feel that you understand more deeply what the heck is going on. There's less magic to all of it. And as a foundation, then you're ready to do a whole bunch of things. Like if I could pop up, I don't have it in front of me, but if I could pop up the graph of courses, after 107, there's a million arrows pointing out to all the other stuff. Yeah, question?
Would you highly recommend 107 before like internship season and applications or something?
Oh, take 107 before internships? Yeah, go ahead. You can speak to that, yeah.
Okay, so I did not take 107 before my first internship. So my first internship was I was learning like basically a bunch of the different tools you need in 107 and that they teach you in 107 before my internship. And so this basically meant that I spent my first week of my internship trying to learn like the first several weeks of 107 and also my internship. So I would strongly suggest learning. It made 107 a lot easier though. That was the advantage. But I would strongly suggest trying to do 107 before an internship if you have space in your schedule, because it will at the end of the day make your internship easier because you'll have better debugging skills and you'll just know the tools that you'll be using in your internship. Specifically Unix, that's probably the biggest one, like learning how to use terminal to do things.
Mm-hmm. Yeah, and Ashley mentioned another thing, which is in the last year or two, they have been looking at the class and trying to make some of the assignments more accessible. They are aware that some students find it to be really challenging, and I think they've tried to add more support, more help, more clarity of instructions on the specs. Some of the homeworks have been revisioned to make them a little more understandable or have more milestones. So I think that some of the bad rep of this stuff is slightly out of date. So that's a little bit about 107. I hope several of you will consider taking it. There's also the variation of 107, which is called 107E. The E is for embedded. Embedded, you learn how to program for a little mini computer called a Raspberry Pi. And so you actually write code that runs on that computer. And it's kind of interesting because, your code is the only thing running on that whole computer. Like you turn it on and it immediately runs your program. Like there's no operating system, there's no terminal, there's no GUI. It just immediately runs your code. And it's funny because like you get really excited when you make like 3 lights turn on and blink. You're like, yes, the light blinked, I did it. It really brings you down to these simple things. Like, I suspect I will be experiencing this with my baby. Like the first time that she like picks up a piece of food and puts it in her face, I'll be like, yeah, that's going to be you when you get a light to blink in 107E. It's a little smaller course because they have to do these labs where everybody sits there with their little devices, and so they don't scale quite as quickly as 107 does. So you have to apply to get into it. They are teaching it next quarter. If you're interested, you can apply to take it. They're both good classes. Students ask me, which one should I take? The regular 107 has been around longer. It's probably a little more of a well-oiled machine, a little bit more polished. 107E, sometimes the code has starter code has a bug, or the spec has a typo, or something's a little bit rougher around the edges or something because it's newer. But hey, it's an interesting new area that like a lot of students are interested in these devices. It's just an interesting domain to learn a lot of the same. You learn basically a pretty similar set of things. So they're both equivalent in terms of what you can do with the things that you learn. Like there are some funny things that happen when you work with embedded devices. Like your code doesn't work, and it's because literally you stuffed the Raspberry Pi in your backpack and you bent one of the pins or something. It's like you actually damaged the hardware. You know what I mean? Like you can have a chip that's faulty, and like so your code doesn't run, and it's because of the chip or whatever. So that's fun. But anyway, there are 2 options here. So if you thought my description or Ashley's description of 107 didn't sound exciting enough, 107E might tickle your fancy. But as I say, I really think the appeal here is there's so many things. If you get this base of knowledge, there's so many things you can put on top of that, which are really fascinating. One more class I was going to ask for your opinion on is CS 103. That's the theoretical introduction in our major. It's called Mathematical Foundations of Computing. This course has a little bit of coding, a little bit of programming, but it's mostly more like a math course with pencil and paper, proofs, algorithms, these kinds of things. And the reason that we study that is because this is really the core of what computer science is. Computer science isn't really about, for loops and if statements. It's more about like the limits of what computers can compute and the nature of computation. And so you learn some really fascinating things about, logic, and you learn, in our theory track, you learn about probability, you learn about models of computation and what they can do and what they can't do. You learn how to make proofs that if I can do this, then I can do that. If I can't do this, I can't do that. You learn about the limits of kind of what a computer program can do. There's all kinds of really interesting things. There are some really fascinating open questions in our field. And one of the cool things about computer science is that it's a really young field, and so we haven't figured everything out yet. There's a whole bunch of big open problems in this area that we don't know the answer to. And if you figure it out, you will be rich and famous, and everyone will be impacted by your work. And don't laugh, that might happen. That might be you. It'll be from a place like this probably if that happens. So that's what 103 is. Now, I will tell you, in the wrong hands, a class like this can be dry. It can be just kind of math and proofs and stuff like that. But the good news is that we've got some of our very best people teaching this class. Keith Schwartz is spectacular. He teaches this course a lot. I don't know what is in his bloodstream. I want a transfusion from this guy. He's got so much energy, and he's a brilliant teacher. He's exceptional. And Cynthia Lee, who's another fantastic instructor in our department, has been working with him, and she's also teaching it. And they're both great. Cynthia is one of the nicest people in this university, and she'll take care of you, and she'll help you when you need help. And so this class, one of the strengths, I think, of our department is we put some of our very best in this class where students need it. So, Ashley, do you have anything you want to add about 103?
Yeah. Okay, so full disclosure, when you're a CS major, you can choose a different track to specialize in. So I specialized in theory track because I took 103 freshman fall, and I loved it so much. I took it before I took a programming class here. Like, I came in and took 103 and decided to be a CS major. That's how much I loved this class. So I came in, I kind of thought, if you're a good enough programmer, you can make a computer do whatever you want. In this class, you mathematically prove that that is not true, which is really cool. You get into questions of like, does it take roughly, one of the, there are a couple different problems you've probably seen before of like, can you write a computer program to solve a Sudoku grid, right? So is it just as hard to write the answers to Sudoku as it is to just verify that a given Sudoku board is valid? Or like, is it just as hard to find the bombs in Minesweeper as it is to verify that those placements are valid, sort of thing? So this is a really cool class because you get into a lot of these different questions. It sets you up to take other really cool classes on like data structures and algorithms. So if you thought that graphs were really cool, or some of the tree stuff that we talked about were cool, or some of the other data structures that we talked about in this class, and like how these data structures work behind the scenes and their big O, and how we got those big O, like this class doesn't talk about it as much, but sets you up for other classes that talk about it a lot. So I'm a huge fan of 103. Both Cynthia and Keith are fantastic people and fantastic lecturers, so I would strongly suggest taking this. One of the coolest classes I've taken at Stanford by far.
That's a sales pitch. Yeah, fascinating stuff. I also think one of the interesting things in this class is you learn about problems that are similar to each other in difficulty. And so you learn like, hey, if I can make a mapping from this problem to that problem, then anything I know about that problem, I also know about this problem. And that helps you make proofs of like, this problem can't be solved in a reasonable amount of time because that one can't be solved in a reasonable amount of time. And this one's basically the same as that one, or it can be converted into that one. And so you can do these real cool things by like talking about nature of problems, nature of algorithms and computation. So it's really fascinating stuff. They will make it interesting and fun. So I guess you could probably sit for a minute. I think we're good. Yeah, thank you. So there's lots of other cool CS courses. CS9 is a great one. You might want to look at this fall. Every fall we offer this class that's all about preparing for technical interviews. I'm sure a few of you would like some help with that, right? So they have people come in and give you tips. They do resume workshops. They have practice interviews. They have practice exercises that you do. CS9 is awesome. Check for it. It's only offered in the fall. That's because the recruiting season, that's the right timing for that class. There's a whole bunch of CS classes whose numbers are less than 100. Those are usually student-initiated classes. Now you might say, student-initiated, what? That sounds Bush League. I want real classes. Well, or maybe that's just me. But no, but a lot of these are quite good. And a lot of them teach practical things that we don't have a course for. Like I want to learn how to code in Python or JavaScript, or I want to learn how to use MapReduce framework for computing at scale, or something like this. You know, a lot of these classes kind of teach you these little practical skills that you might want to learn. CS50 is fascinating. It's a CS for social good. There's some other courses with 50 in the number that are in that same vein. If you're looking for like, how do I take this coding stuff and CS stuff and use it for something real to help people, to make the world better, that's where you want to start. Go to CS50 website and look at what they're doing. They have interesting projects that actually really directly affect lots of real people. Here's some courses in the, in the curriculum that I find fascinating. I want to be a little careful not to over-recommend anything because everyone's interests are different. So, I'm a coder, a hacker, so I'm interested in coding and web apps and Android apps and iPhone apps, and so there's lots of courses if you want to learn those kinds of things. The HCI course 147 is great if you want to build something bigger. You want to spend the whole quarter designing and building a bigger system, and you can learn about that. Another course number in general that you might want to watch for is 193. This is kind of a catch-all number for whenever we have a special topic that we want to offer that doesn't fit in another category. So like our mobile app course is under that. And if we, sometimes just some random professor will say, I want to teach a class on deep learning. Okay, well, we'll call it 193K or something. So, every quarter, every year, maybe look at that course number and see if anything cool is listed in there. So those are some of our courses. I've only got a few minutes left, so I kind of want to just zip through a few things. If you like this class, hey, maybe the other nicest compliment you could pay me would be consider majoring in CS or minoring in CS. It's a good major. A lot of people care about teaching in this major. We'll take care of you. We're basically the #1 school in the nation in CS, and you'll get a good education if you want to do our major. You can minor in it. If you want to look at the minor, you can look at that same webpage. Basically, you take 103, 107, the ones I mentioned, plus 2 or 3 more classes. You can minor in CS. It's a great add-on to whatever you're doing. If you're a sophomore or junior or something and you're saying, I don't know if I have time to switch to my major or whatever. Well, minor, get a minor. It'll look great if you've got bio plus tech or econ plus tech or whatever you're doing plus tech. I bet that'll look great on your resume. We've got a coterm if you want to do it for grad school. Like if you're a senior and you're like, it's too late for me. Well, maybe not. Maybe not. We've got these other majors I don't have a ton of time for, but these other majors that basically are tech, that encompass tech with other things. Tech plus logic and AI, tech plus business, tech plus math, tech plus electrical engineering or hardware. There's all kinds of stuff that's like us plus something. Chocolate plus peanut butter, it's even better. So if you like this, but you have other things you want to do, we might have a major for you. Couple quick things, I'll just zip through this. If you want to learn some more stuff, there's lots of good things online. There's online courses, there's online tutorials, there's online practice. This is a great field for just teaching yourself something. I wonder, how do you write an iPhone app? Go figure it out. It's all up there somewhere for free. If you want to get an internship, you probably already can. You probably can go talk to companies. A lot of companies want people with only your level of expertise. They really do. Because they want to build a relationship with you so that when you graduate, you'll go work for them. Because it's so competitive to get people, so hard for them. They want you guys so bad that they want to talk to you as soon as they can. So if you want information about internships, go to forum.stanford, sign up for their mail list where they send out industry announcements about jobs and ads and tech talks and stuff like that. I have some links on these slides you can look at later. These are a bunch of companies that have internships specifically for freshmen and for people who haven't taken very many classes. So they're not going to be competing you against some junior or senior. These are for you. And I've got a couple pages of them here in these slides. You can look at this later, maybe over spring break. They're taking applications for summer if you want to look at these. Lots of big companies and small companies alike are looking for you. So check it out. There's a few more on this slide as well. Last couple things I want to say. You can teach yourself lots of fun stuff. Think of something you want to do and go try to teach yourself about it. Learn how to make a website or a mobile app. Try to learn a new language. Rewrite a 106B homework in Python. See if you can do it. Let me jump ahead a little bit here. So the other thing is I hope some of you will consider applying in the future to be a section leader. We need more people, and you're already qualified. We want people like you. If you like this class and you want to help other people, maybe you help somebody in your dorm, you help somebody in the lair who was stuck. Great, we want that. We want you to do that. We want to pay you for that. We pay pretty well. We talked about that a few weeks back. Maybe you can sign up to do it for the fall. I wanted to take a second to say, this quarter was a unique one for me, as you know, because of my little baby. And that was tough. I had to be gone a lot, and it was hard to juggle that and this, and I didn't want you guys to really suffer for that. And that was only really possible because of the tremendous work that my two head TAs did. So I hope you'll join me thanking Ashley and Amy for their great work. Actually, I got a little something for you in my office, a little gift I want to give you later. I didn't bring it because I was going to lose it. I'm so clumsy. But I also want to thank the section leaders for all their help. They're not here, so you don't have to clap for them, I guess. But for all the great help they give you in the lair and otherwise, the section leaders are exceptional. And thanks a lot, guys. Good luck with your studying. See you Monday.